Hey Chem students, I'm here with lesson 2. This lesson focuses on free energy and spontaneity. I introduced spontaneity of reactions in the first lesson on this chapter, but we're going to dig into it quite a bit more right here. So our outcomes for this lesson, the first video, this one, will really focus on the concepts. These definitions are pretty tricky. Just wrapping your head around the concepts is our goal for this first lesson. Then the second and third lessons will be problem-based, some example problems of how to use that information. So to define this term free energy, let's actually circle back to spontaneity. Spontaneous reactions happen without energy input. If we think about a bonfire or campfire, a lot of energy is being released there. And this type of reaction is actually favorable in terms of both the enthalpy and the entropy changes. So we know that this bonfire, this campfire, gives off a whole lot of heat. It's exothermic. So from an energy point of view, if the reactants are up here in terms of energy and the products are down here, we're getting to a more stable, lower potential energy situation over the course of that reaction. So exothermic reactions tend to be favorable. Entropy in this campfire, in this bonfire, certainly matter and energy are getting dispersed. That's also favorable. So it makes sense that a bonfire, a campfire, is a spontaneous reaction. We talked about the ice melting, which even though obviously it's spontaneous, is a little trickier because that's actually an endothermic reaction. So I talked a little bit about that in the last video. So we need to consider both of these things, both enthalpy and entropy, to be able to determine the spontaneity of the reaction. And so when we, to define free energy, which we symbolize with a G, it's really the portion of that total energy change that's free to do useful work. Now, that's pretty hard to wrap your head around. Mathematically, we can combine that enthalpy and entropy term. And when we combine those in the form of delta H minus temperature times delta S, that gives us our free energy change of the reaction. So one way to think about this is that those entropy changes are almost like a tax on how useful the energy can be. Matter energy that's dispersed can't really be harnessed all that well. And in fact, a little history, these state functions and this free energy term were defined back in the days of the steam engine. And it was really out of necessity that people came up with thermodynamics. They were saying, hey, we're putting all this energy into our steam engines. Why can't we get all of it back out? And the answer is because entropy is a tax on the system. So let's think about the signs on these terms. And reaction change in enthalpy over the course of a reaction, delta H, also called heat of reaction or enthalpy of reaction. You learned that last semester. It's essentially just how much heat is released. And like I was saying with the hand motions earlier, if we're starting at one energy level and ending at a lower energy level, that's an exothermic reaction. That's a drop in energy. And so the sign on that exothermic reaction is negative. If it's positive, then we have an endothermic reaction. We have to put heat into the system. Entropy we defined in the last lesson, and because we define delta terms as final minus the initial, if it's positive, that means that entropy is increasing. Our matter and energy are getting more dispersed. If it's negative, entropy is decreasing, and the system is becoming more ordered. So looking at that key equation, so we already defined what kind of counts as favorable in terms of enthalpy and entropy. We know that a negative value for delta H, that exothermic reaction is favorable. And we know that increasing entropy is favorable. So positive values for delta S. So if those two things are favorable, mathematically, we're getting a negative value here and then we're subtracting a value here. That means that when delta G is negative, our reaction is spontaneous. When that free energy is decreasing, we end up with a spontaneous reaction. Opposite, if our reaction is endothermic and our entropy is decreasing, that's definitely going to be a non-spontaneous reaction. So when we see a positive value for delta G, it's non-spontaneous. One way to look at this is that reactions tend to occur to minimize the free energy. So we already kind of went through the signs on delta H and delta S that always lead to negative values for delta G. So spontaneous reactions at all temperatures. And we also looked at the opposite scenario. Positive value for delta H, negative value for delta S. We're always going to have a positive delta G, leading to non-spontaneous reactions. But if we have either both positives or both negatives, then the reactions may be a little bit more complicated. So if we have, let's say, an endothermic reaction, so a positive value for delta H. Good example here is one of those instant ice packs. You kind of shake it or you squeeze it and it gets cold. That's endothermic because it's absorbing the heat from your hand. Yet we know that's spontaneous because it gets cold right away. So if that's spontaneous, we know that delta G has to be negative. And the only way this works out mathematically is if our delta S is big enough such that we're subtracting this term here and that overall value ends up being less than 0. But you can see that temperature is involved as well. So the value of the T, the temperature, is going to have an impact on whether or not our delta G is negative or positive. So bottom line, if that T is bigger and the entropy is fairly substantial, it's more likely to end up with a negative value for delta G, leading to a spontaneous reaction. At lower temperatures, there's some threshold where as you're lowering that temperature, this reaction is no longer going to be spontaneous because that term there is not big enough anymore to create a negative delta G. So one thing we sometimes say is that a reaction that is spontaneous is being driven by those entropy changes as opposed to the positive value for delta H. The last situation, if both the enthalpy and entropy are decreasing, that means that this is an exothermic reaction, and it's driven by that exothermic nature to still be spontaneous. But at some point, we reach a temperature high enough that the reaction is no longer spontaneous. So we're doing a little experiment now, a little demonstration. I want you guys to all pause it and grab a rubber band. Anything, the wider the better if you have a couple lying around. So pause the screen. Did you go and get it? I don't believe you. Pause the screen, go get it, and come back with a rubber band. All right, let's say that you got it now. What I want you guys to do is take the rubber band, put it on either your lip or your forehead. So I'm gonna put mine on my lip. And then I want you to stretch it out. And it's still touching my lip. Did you feel any temperature change there? It's not super drastic. But it's noticeable that when you stretch out that rubber band, it feels warmer than it was before, the rubber band. You can try it on your forehead too. You can also try it the other way. If you stretch it out and put it on your forehead, and then let it go back, it noticeably feels cooler after you do that. So let's think about what's going on here, and I'll think about it from the stretching term, first of all. And I think this is just kind of a good way to sort of illustrate this relationship between free energy, enthalpy, and entropy. So we're actually looking at this, the act of stretching the rubber band. This is not like a chemical reaction that we're looking at here. So first question for you guys, was stretching the rubber band spontaneous? I would say it's not, because I had to actually do something. I had to pull on it. I had to work that rubber band to make it stretch out. So I'm going to call that non-spontaneous. And then the enthalpy change, what did we feel? So when I stretched it out, it got warmer. That's a release of heat that I'm picking up with either my forehead or my lip. So that delta H term is negative for stretching the rubber band. So the only way this equation works out is if delta H is negative, but my reaction is non-spontaneous, delta G is positive, this number, when subtracted, must counterbalance that negative delta H. So that means that this entropy term must be negative as well. If I subtract a negative, it becomes positive, and so that could give me a positive value for delta G. So let's just try to think if that makes sense. Am I lowering the entropy of the system? Am I making this less dispersed when I stretch the rubber band? Or less disordered or more ordered, I guess is the easiest way to state that. Well, let's think about what this rubber band is made out of. Rubber molecules are big, long, complicated polymers, and they are very windy. And so when I stretch out those rubber molecules, when they're not stretched, they're all kind of wrapped around each other, and there's all sorts of permutations, all sorts of ways that they could be oriented. But when I stretch it out, they kind of line up. This picture, I think, demonstrates it really nicely as well. So yeah, when it's unstretched, all these molecules are tangled with each other. And there's about 1 billion ways that these things could get tangled. Thinking about entropy as related to the number of possible orientations and places that these atoms and molecules could be in, there's a whole lot more disorder here, a whole lot more entropy here than there is when those chain molecules are stretched out and untangled from each other. So I think that rubber band analysis is really kind of just illustrates how that equation, how that relationship works. But yeah, also goes to show that even just something as simple as stretching a rubber band, you're causing changes in entropy and in enthalpy and free energy.